Today I am discussing Gattermann Koch reaction. This reaction is similar to Gattermann reaction. The difference between Gattermann and Gattermann Koch reaction is that in Gattermann reaction HCN with HCl is used to produce a electrophile, while in Gattermann Koch reaction carbon monoxide molecule is used with HCl to produce a electrophile. Both reaction uses aromatic substrate as a nucleophile. Aromatic substrate can act as a nucleophile because they have high electron density on their surfaces, and this electron density can be used to attack the electrophile. In Gattermann Koch reaction, when carbon monoxide molecule is used with anhydrous HCl, aluminum chloride acts as a catalyst to produce a electrophilic species, and this electrophilic species reacts with aromatic compound to produce a aldehyde molecule, and the aldehyde molecule is usually a aromatic aldehyde. Aldehyde group, that is CHO, is introduced in this reaction. This group is also CHO group is also called a formyl group. So, this reaction introduces a formyl group in the aromatic substrate. The reaction, this Gattermann Koch reaction is not applicable to aryl ethers. In place of aluminum chloride, one can also use ZnCl2 with a small amount of cuprous chloride. Now, whether one use ZnCl2 or aluminum chloride, the condition has to be anhydrous condition. Under aqueous condition, these catalysts won't work. Under aqueous condition, water is present. Water has oxygen, and oxygen donates its lone pair to d orbital of these metals, and once d orbitals of these metals are occupied, they won't act as a catalyst. The mechanism of the reaction involves reaction of carbon monoxide with HCl. As we know, carbon monoxide has a triple bond between carbon and oxygen. Oxygen has a positive charge and carbon has a negative charge. The negatively charged oxygen accepts a proton from HCl. HCl is acid, so it can donate its proton easily, producing a species like this. In this species, in the product, positive charge is present on oxygen atom. A negatively charged Cl minus ion is also produced as a product. Oxygen has a positive charge, but it won't act as a electrophile because oxygen cannot make a fourth bond. So, what it does is that it withdraw electron density from carbon. So, carbon becomes electron deficient. It also takes, oxygen can also take electron of pi bond to get neutralized. That means, its positive charge disappear after receiving these pi electron, and this process generates a positive charge on carbon. Cl minus acts as a nucleophile and attacks the carbon, producing a species like this. So, in this species, oxygen has no charge and carbon has a hydrogen and a Cl. Now, this species, this product interacts with aluminum chloride we know that Cl has 3 electron pairs. These electron pairs interact with d orbital of anhydrous aluminum chloride. So, these electron attacks the aluminum. So, it leads to generation of a weak bond, and when this weak bond is forming, aluminum develops a negative charge and Cl develops a small amount of positive charge. So, because Cl has a small amount of positive charge, it tries to take all the electrons of carbon Cl bond. So, these electron moves towards Cl. So, carbon Cl bond weakens, and Cl aluminum bond strengthens. So, these electrons, we can show that these electrons are moving here, forming a stronger bond, and then electrons present on oxygen go and form a triple bond with carbon. So, this reaction step produces a electrophile and AlCl4 minus. Now, HCO is electrophile. Again, oxygen won't act as a electrophilic center because it is already having 3 bond, it cannot make 4 bond. So, what it does is that it can accept pi electron, generating a positive charge on carbon. One can also show this like this as a resonance contributing structure. So, when these pi electron moves to oxygen, one generates a, or this species generates a positive charge on oxygen. As you can see in one of the resonance contributing structure, carbon is having a positive charge. So, it is electron deficient. So, this species acts as a electrophile. Now, aromatic substrate comes as a nucleophile. Its electron density attacks the positive charge on carbon. One can show attack like this if you are using this species as a electrophile. If you want to use this species as a electrophile, you can also show it like this: H C double bond O with a positive charge, aromatic substrate, and then these electron attacks carbon, and when this species is attacking carbon, these pi electron shifts to oxygen. Both the process produces the same species as product of this step. So, there is a positive charge here and C double bond O H. Now, this is not a aromatic species, this is not a aromatic species. So, there is a proton here. This proton is accepted by either Cl minus, that is there in AlCl4 minus, or some solvent. So, some negatively charged species takes this proton, and then these electrons which are here, they moves and forms a pi bond. This way the reaction or the reactants achieve its aromaticity, or reactants achieve their aromaticity, producing the product. So, this ends the reaction mechanism for Gattermann Koch reaction. If you have any question, feel free to comment.